Merci, Daniel. Okay, so today I will speak about two topics. One of them is last year I did contribute to the dispatcher module latency monitoring. And then the next step that I was having in mind was to use this information to influence the dispatcher algorithm. So I will cover all these points in the order I have selected. First, I will explain how you can use the latency monitoring and how we identify congestion, the estimated congestion a gateway is facing. Then I will explain the benefits of the new algorithm, the one I see, and then I will explain how you can configure it once it will be merged, because the merge request should be done probably this week. I was hoping to share all of this so that it could help with the review process and I could gather feedbacks if anything was not well handled. And then we'll move on to the expected behavior, knowing how the algorithm is doing his work. We'll take two examples of with one or more congested gateway and with all of the gateways being congested, what's the behavior? And finally, the most difficult part was all the testing in a laboratory to test that everything was working as expected, and that in real life, when a server becomes saturated in resources, you still have this period where you have an increased latency, and you can usually so using a real-world saturation of CPU, and I can prove that at least in many cases, the dispatcher will have some time to react before it's too late, minimizing the congestion. So this is already in Kamailio. Now you can monitor your gateways by setting. You need to have the ping set, the SIP option ping, which is an old feature. And then you need to activate DS ping latency stats. And at this point, the dispatcher will start to compute the statistics every time it's receiving an answer to a SIP option, or if it's timing out. And then there will be, in the latency section at the bottom, you see that there is average, which is since the server started, or if the dispatcher was reloaded. So of course, there may be some, when you reload the dispatcher, you lose the statistic right now. This may not be the best option. The standard deviation of this average. And then the EST, which is simply an exponentially weighted moving average. And you can configure it by, with the mod parameter DS latency estimator alpha. This is well documented on Wikipedia or anywhere for those who haven't used an exponentially weighted moving average in the past. It's on the scale of, because Kamailio doesn't support float in the parameter, it's in the scale of 900 to, it's on 1000, so that you can get precision. And yes, so this is how you can control the responsiveness or the memory. We'll speak about it a little bit later for those who don't know much about these estimator. You can find one of these exponentially weighted moving average in RTCP, for example. The enter arrival jitter is using an exponentially weighted moving average of 1/16 is added to the. So the enter arrival jitter is trying to tell you what's the recent jitter you are facing during a call. So it's the same very basic recursive estimator, really easy to mathematically to implement in a code, in source code. So in this fictive example in red, you can see right now what's the estimated congestion in milliseconds. So mainly it's the average since the server started. This is the best information we have on how this gateway is supposed to respond in terms of latency. So in this case, it was 72 milliseconds on average. And then suddenly the EST, which is the exponentially weighted moving average, is telling us that, wow, at the moment it's slower than usual. And it's the estimator will ramp up slowly or down depending on if it continues or not. But at this time, what we can tell using this estimator is that we are 26 milliseconds above the normal performance of this gateway. So this gateway is underperforming, and it's kind of worrying. And then the timeout, you can, the DS ping will time out based on the FR timer. So the default is 30 seconds. So it won't time out very often, but just, now, why do I think this new algorithm is valuable? The main objective is to avoid using gateways that are congested or that are likely to be congested. And the benefit we get is that if these gateways are indeed congested, then not only signaling will be affected, we'll have less time to fail over, but also the media. Many gateways, they do, like Acme Packet SBC, most of them, they handle media on the same box as signaling. It doesn't mean that because the signaling is slowing down, the gateway will also be slowing down in general, but it's likely. If it's because the server is logging too much, because the internet connectivity of this gateway is now problematic. So it's kind of it's very likely that if a gateway has hard time to respond to signaling, it will probably have not be that good with dealing with media, which is even worse. So right now, what's the alternative? The alternative is to detect the gate. One of the best option I think we have right now when facing problems with gateway is to configure the dispatcher to ping them on a regular basis. And then when it times out, it will just put them out of service. So here we have the 4 settings where you can say how often it will ping them. Once again, what's the timeout? We change it here, but it can be changed, overwritten in the routing script. And then how many times should it fail before the gateway is out of service, and how many times it has to recover. So this is configurable, but now which configuration are you setting? Because depending on what you're setting, you can get, for example, what I identify as limitations is if you put them too low, let's say the FR timer is too high, then you have to wait for it to trigger. So during this period of time, a big batch of call could be sent to not the most effective gateway. And then if you set it too low, on the other end, a little network glitch could leave you out of gateways because all of them could be put out of service. And the other drawback is if the problem is intermittent, then it will time out, come back in service, time out, come back in service. Then most of the time you're taking the wrong decision sending to the gateway. There's no memory in this. Well, with the exponentially weighted moving average, you do have memory. It's providing, because it will slowly ramp up and come back to normal, so it won't forget immediately that there was a problem 5 or 10 seconds ago. So this is why I think the new algorithm could improve things. How do you configure it? Mainly, you use the same settings that were used to monitor because it's using the metrics. And then you just tell him, yes, use congestion control here. And then you use the algorithm 11 because algorithm 11 is using relative weight-based load distribution. The big thing is if one gateway is removed from service, it's redistributing the weight proportionally on the remaining gateways. Well, the other algorithms had this problem where one of the gateway was taking too much traffic. This one is improved, and I could just reuse the code where it's redistributing the weight proportionally. So I not think the patch, in fact, is very small to implement this now. And I don't think the other algorithm are worth, the ones that are not doing this relative weight-based load distribution are not good candidates. So how do we impact traffic sent to a gateway based on the congestion we are estimating? We use the weight parameter. So 1 point of wait it will accept 1 millisecond of congestion. 50 milliseconds is a lot of congestion in the estimator because it will ramp up. So if we are too tolerant, it will take too much time. But this could be configured based on how long you want to wait. So in fact, the wait will let you decide how much congestion are you willing to accept before you start moving the traffic away. So in this case, if there was 10 milliseconds of congestion estimated on one of these two gateways, it will go to 40 instead of 50, and then it will take let's say 30-something% of the traffic. The weight will be redistributed amongst them. So what's the expected behavior? In fact, I just explained it. Let's take a fictive example where we have an estimated latency of 85 milliseconds, and we know that this gateway should perform at 60, because since it was running, it was showing 60. So we know suddenly it's slower. And so we do what I said, we remove 25 points from the weight. And as we see with this example with 3 gateways, only one of them is showing latency. So suddenly, it will just receive 20%, and the traffic will start to move away from it. Maybe this could help the gateway. If we were the source of congestion, we'll know the estimator will automatically continue to learn from this gateway and will move the traffic, more traffic away. So most of the decision is based on the estimator, in this case, the exponentially weighted moving average. So, but this is the expected behavior when one of the gateways is facing congestion. Now, when it will reach 50, this gateway will be removed from service, but it won't be removed from service permanently. If all the others gateways are also congested, then there is a second pass, and suddenly the load is redistributed based on the ratio of congestion. So now all of the gateways are congested, so they are back to in service because they are our best option. And at this point, we will load balance based on the ratio of congestion each of them is facing. And then, of course, one of them could be brought out of service finally because the ping will finally fail and time out. So at one point, they will be removed, but we are proactively taking decision to move traffic away. So if you are using carrier gateways and each of their gateways can take all your traffic, then it's an easy pick. You don't really care. But of course, if you are load balancing to your IVR servers, transcoding servers that are optimized, then maybe this algorithm is not as straightforward because you could create issues by overloading one of your server. But I'm just showing some use cases. So in this case, one of them was having 50 milliseconds of estimated congestion, the other one 75, and the other one 100. So it's proportionally load balanced to try to minimize the impact and send traffic to the best performing gateway. So this is the lab I did set up to test all of this. There was 4 gateways and 2 clients. 400 CPS passing through the Kamailio load balancer, and another one sending like another source of traffic to overload even a little bit more one of the VoIP perf server. The servers in red will be affected by the stress application that will create resource utilization on the server, like CPU, doing all kind of routine to overload the servers, resources to load the CPUs, memory, and I/O, to try to create something like real-life performance problems. And then this is the scenario. The first 20 seconds, nothing happened. Then there is a little problem on the servers in red. Then there is no problem again. Then there is a big problem. Everything is completely wasted on the server. Not everything, it's still responsive, but it's really saturated in many ways. And then we are back to no problem to show that we can recover quickly from these problems. We won't be stuck in a bad state. So this is one test. This one is with the dispatcher is configured with a timeout value of 1.5 seconds. So at one point, it will discover it may time out and remove a gateway from service. So on your left side, right? On your left side, you have the version with congestion detection. The graph at the top is showing the responsive time per second. So each sample is 400 calls. It's the average time it took to receive a 100, a 180, because the scenario is we call and then we get a ringing and we get the answer after all. And then we also disconnect, but I'm not monitoring the disconnection. But in this case, yeah, we can see that the 100 trying, of course, were completely stable. Kamailio was not facing any problem. It was running on a performance server enough. And then we see the two problems we were expecting. One of them, the first glitch, and then the bigger glitch. And we can see that they are not aligned, unfortunately. So normally they should be well aligned. Like this would match this problem, and this one would match this bigger problem. And what we can see is that the gateway number 1 and 2, where we did detect problems, and gateway number 2 was having more problem. So as we can see here, gateway number 2 is loaded with another extra 150 CPS, so it's normal that it's experiencing even more problem. And then on the other side, we have what we would get with the normal timeout, quite aggressive timeout of 1.5 seconds. In this case, you can see we have to wait 2.5 seconds sometimes to get the connection. So the impact was greatly minimized. Many calls were connecting faster and connecting to other gateways. So it was more responsive to move traffic away. And then we have a little summary, but of course, because the problem was only lasting a fraction of the time, but still you can see overall what was the average response time of these. There was no timeout from the VoIP perf client, but the dispatcher did trigger once. In this second test, the dispatcher will never time out because it's using the default 30 seconds. So it's just another test. We can see the same pattern is repeating itself almost on the side with the congestion detection. And in this case, there was some timeout. After all, the VoIP perf client was reporting timeout. It was waiting too long for the. And this is another test where what happens if all the gateways are congested at the same time, just to verify that everything is working as expected. So you're using NetM, I just add enough milliseconds to disable all of them at once by going above 50 milliseconds. And then I run the same test. So yeah, the adaptive behavior is kind of almost the same. We can see that it's detecting that gateway number 2, the red one, is really facing more problem. So it's receiving far less traffic, and then gateway number 1 is also problematic. At the beginning, there is some glitches because the estimator is now, they are put out of service one by one. But then it recovers, and it finally learns that they are all out of service, so bing bing is something like that. Okay, so now the load distribution is based on the, so you can see the difference without, this time it was up to 4 seconds to process all the 200 OKs. Yes, so a little more about the tools I have used to do these tests. The VoIP perf tool is forked from a sample application in PGSIP. So you can see one command where you can randomize the phone numbers and force a call per second. So it will really try to do the call per second there. It will try to distribute it in a second to avoid sending everything in 1 millisecond. And it's multi-threaded. It's really, you can do several thousand CPS on a type 0, packet.NET type 0. This application is incredibly fast and compliant. And this is the output of one of the tests where you can see simply each of the tests I was sending 50,000 calls. So it's just confirming it it's the default output the application is giving. But inside the file, it's also providing latency information per period of time, the interval at the top. So every second, it's outputting the standard deviation, the average, the maximum value of all of the responses received. So this is how I created the graphs. Just like CP can do these things in a CSV file. But this one, you can configure the interval. So if, I don't know, I think with CP, I'm not sure you can anyway. And how did I orchestrate all of this on these servers? It was a lot of work to start. I used tmux with a little shell script. So it's starting the pane inside the window in tmux and starting the application. So it's really easy to reproduce the test, making sure everything is quite synchronized. Yeah, so I'm sharing every result and test I have made. They are shared in a GitHub repository just for future reference, and because it's really time-consuming to do these tests and save the output. Then VoIP is also an application that is available. Yeah, the presentation is. So I guess I will just put a merge request in Kamailio, and then we'll discuss it further. And
yep.
But
okay, question I have right here.
When the latency is when the latency is detected, would it trigger like the down route so that you could do custom alerts or anything?
oh, no.
Right.
But you could still have a script to monitor it yourself. Like here, I forgot to mention, in Datadog, we are monitoring it. The latency stats from last year, we are using them. So these are servers in the same LAN. They are below 1 millisecond most of the time. But we are also monitoring carriers, and we saw some, we did once in a while face a malfunctioning carrier switch, whatever, and it was, it was showing intermittent, of course, latency in this case. So no, sorry, there is no callback, but at least by monitoring them frequently, nothing should stay unnoticed. In a little article on the Kamailio website, you can see a Python script I have used to extract the information. Because right now, unfortunately, the only interface is the dispatcher, this format. Maybe we could add a command to have a better formatted output, than using this proprietary format for extracting.
Yeah. Okay, Giovanni. And maybe you can prepare for the next presentation. No, no question without microphone.
I'm looking right now in the GitHub for the VoIP program that you just announced, and seems very, very, very interesting. Can you spend a couple of words about?
Yes. So. In fact, the prototype was made by the PJ SIB team. So in the end, all the optimization was already made. It was really, really fast. So what I added is the latency monitoring mainly. And then I don't remember now everything I've modified, but for them, perf is pushing as hard as you can to get your magic number, right? Like, what's the other perf application? For me, it's more, I know my magic number and I want to make sure everything is working well. So 1,000 CPS, I'm just sending 1,000 CPS for 1 hour, and then everything should be LT. The application by design was more push as hard as you can until yeah.
Okay, so Julien is going to be here around and on mailing list. Again, one of the very active developers and really good contribution lately. Thanks again for everything and for taking the time to present this. I'm sure people will find useful and maybe will start contributing to your VoIP perf application as well. Thank you.
Thanks.